All right, so we're on to the mini lesson number 3. Here's our 3 learning targets. I can explain how elements of different electronegativities share electrons. I can determine the polarity of covalent bonds. I can explain how the pairs of electrons determine the shape of a molecule. All right, so if we go to, so this is a periodic table. Slightly different than the ones that we've been looking at. These numbers below represent the value of electronegativity. We've talked about the trend of electronegativity. Now we're going to actually talk about these values. All right. So you can see by looking at this that the most electronegative atom here is fluorine. All right. And we look at electronegativity, we're looking at, remember we talked about this, the affinity of an atom to pull electrons. All right, so it makes sense that these guys in this column here all want electrons, right? They're one away from being stable. And we remember from previous quarter, the trend in electronegativity is that electronegativity increases in this direction, okay? So if we start on the left side of the periodic table when we're facing it, and we go to the right, we see that electronegativity is going to increase. And if we look down the columns, we see that electronegativity is going to decrease. So why is that? It goes back to the atomic radius, right? The size of the atoms going down the column increases, right? So the bigger they get, right, the less hold on those electrons. As we go this direction across, atoms are getting smaller. So the nucleus has a stronger pull. Remember, my nucleus is made of my protons and my neutrons, so it has all the positive charge. The electrons are on the outside, that's all of my negative charge. So the further away the electron is, the less pull, right? The closer it is, the more pull it has. So if we look at fluorine, it has the highest electronegativity. One thing you may notice, there's no electronegativity listed in the column for my noble gases, right? They don't really form bonds, right? They don't want any or need any more electrons. It's very rare. There are cases where they can, but for our sake, let's not even worry about that. All right, good job. Okay, now let's talk a little bit about polar covalent bonds and non-polar covalent bonds. So we'll go to the next screen here, maybe. All right. So let's say I have 2 fluorine atoms, right? They have 7 valence electrons and they form a bond so that they form a covalent bond. They each share an electron to make them stable. Now imagine this is a tug of war. Okay, so the pull on the electron, what do you think is going to happen, right? 2 atoms that have the same electronegativity, right? Is one going to pull more? If we think about their nucleus, that's where all the positive charge is. And then we think about the electrons way out here, right? And they're sharing these 2 electrons, identical atoms, right? They both have the same number of positively charged protons, same number of neutrons, which don't matter, and then they have these electrons. So they're going to share those electrons equally, right? So if there's a tug of war, they're matched equally, and they can't pull it any closer. So in that case, we call that a non-polar covalent bond. So we just looked at 2 non-metal atoms that would form non-polar covalent bonds. Now let's look at an example of a polar covalent bond. So we have hydrogen, which has 1 valence electron. Fluorine has 2 valence electrons. So just as a review, how many electrons does hydrogen want? 2. And how many electrons does fluorine want? 8. So they're going to share their electrons and form a covalent bond. Oof. Everything was so straight a second ago. There we go. So now, what would be your guess? All right. So let's look back. So hydrogen up here, they give it a value of 2.1, and fluorine over here, they give it a value of 2, which is going to be what's going to happen here. This is going to form a polar covalent bond. Remember, tug of war, right? Fluorine is smaller. It has more protons, right? It's got 9 protons in its nucleus. It's supposed to be 9, right? Hydrogen just has 1. So this electron is going to be shared much closer to the fluorine atom, which has 9. So in that case, it's an example of a polar covalent bond. Now I know what you're saying. Wait a minute. Why do you put sodium and chlorine up there? They don't form covalent bonds. No, they don't. We remember that they're actually going to form an ionic bond because this electron is going to get transferred to chlorine. Okay, so it is an ionic bond. If we go back to our chart, periodic table. So let's look at chlorine 3, and let's look at sodium 0.9. Let's call that 1, right? So the difference in electronegativity is 2, right? So there are other ways that we can determine the type of bond that's going to form. And one of them is by looking at the difference in electronegativity. So if there's an electronegativity 2 or greater, that's going to be an ionic bond. All right. If we have an electronegativity that's between 0.4 and 2, that's going to form a polar covalent bond. And if it's less than 0.4, it's going to be a non-polar covalent bond. So that just kind of rounds out what we've been looking at. But we can predict, remember, metals and nonmetals form ionic bonds. Okay, so we don't necessarily have to look at those values, but we can use those values to help us determine the type of bond. And in this case, right, chlorine, if we're looking at that tug of war analogy, as no contest. Chlorine just yanks that electron away without even trying. Sodium kind of just like throws it at him and runs the other direction, right? It's transfer of electrons. All right, so we've talked about electronegativity. We've talked about how to use that to predict the type of bond that's going to form, and we talked about the polarity of covalent bonds. Now we're going to talk about the shape of molecules. So this involves a real fancy term. We pronounce it VESPER, and it stands for valence shell electron pair repulsion. I actually had to look that up. But it's a fancy way of saying that we have electrostatic forces, right? We have a nucleus that's positively charged, and then we have electrons. So if we're sharing electrons, right, they're going to have electrostatic forces within the molecule, and they're going to help determine the shape. So let's take water, for example. So we have a water molecule. So there's oxygen, there's hydrogen, it's H2O, right? We know that oxygen has 6 valence electrons, right? So it's going to share its electrons. So it has 1, 2, 3, 4, 5, 6, 7, 8. Hydrogen has 1, 2, and hydrogen has 1, 2. Right? That's exactly the way it wants to be. So these lone pair of electrons are up here. And what they're going to do is they're going to push these hydrogen atoms out of the way. Why? Because this is all negatively charged, right? This same charge is going to push those things away. So if I have, let's say, I have a molecule, here is my central atom and two identical atoms on the other ends, right? So I just have two pairs of electrons. Then in this case, I'm going to have a linear shape. And that makes sense, right? Think of CO2, carbon, and oxygen. Oxygen, right? Oxygen has it's going to form two double bonds, right? So it's going to have this linear shape. If I have ammonia, right? Or actually, all right. So now I just want to show you these different shapes. We call that this one the linear shape. So now we have nitrogen and oxygen. Okay. So nitrogen has 5 valence electrons, right? So it's going to have this 2. It's going to form double bonds with the oxygen, right? 1, 2, 3, 4, 5, 6, 7, 8. Oops, sorry. Do that with 1 of those oxygen atoms. This is one of those trickier ones. Right? So it shares these electrons. We have this lone pair up here, and the point of this is that this lone pair pushes these oxygens down, and it forms what we call a bent shape. Okay. So now if we look at boron, boron is one of these weird exceptions. It doesn't need the 8. And this is a triangular planar shape. All right. So the point of all these different shapes, you could look them up, but I want you guys to see how they push electrons into the positions they should be in. All right. So we looked at this one. This is methane. All right. So we call that the tetrahedral. Try and imagine this in 3 dimensions where the hydrogen's kind of in the back, right? And then pyramidal. This is ammonia. So it's NH3. And then this is water. So water has these 2 lone pairs of electrons, H2O, and those 2 lone pairs of electrons push it down. So this and NO are both bent shape, right? So this is just to give you a sense of how these forces push them into different positions. And it's important to understand how this works, right? When we have molecules form attractions between each other, remember we have how they have to orient themselves in particular position, and we talked about this with phase change and other things. So it's important to understand the different shapes that we form with these bonds. So hopefully that wasn't too quick. Big takeaway here, don't worry so much about the dot structures. We'll have the opportunities to practice that more, but understand how the bonds themselves are going to push atoms into certain positions. That's the big takeaway. So you should be able to go back to your